Hello everyone, welcome to this section of the fifth unit in our course ME22088 Vibration and Noise Control. Today we will be diving into the fascinating world of vibration excitators, which is focusing especially on mechanical and hydraulic types. We will explore how these devices generate controlled vibrations which are essential for testing and analyzing the dynamic behavior of structures and materials. I am Dr. Sendamari, Associate Professor in the Department of Mechanical Engineering at SVC. Feel free to reach out if you have any questions regarding this topic or any other material we cover in this course ME22088 Vibration and Noise Control. Alright, everyone, let me see the fascinating world of vibration testing and specifically look at the workhorse of this field, that is vibration excitators, often referred to simply as shakers. These devices are absolutely essential tools across a wide spectrum of engineering applications. Their primary role is twofold and incredibly important. First, vibration excitators allows us to determine dynamic characteristics of machines and structures. Think about it, how a bridge responds to wind or how a car chases behaves on a bumpy road. These are dynamic characteristics, and shakers can help us to determine and understand them. Secondly, they are crucial for conducting fatigue testing of materials. By subjecting materials to controlled vibrations over extended periods, we can assess their durability and predict their lifespan under real world operating conditions. Over the course, we will unravel the fundamental principles that govern the operation of different types of exciters. Also, we will explore their inner workings and mechanisms that allow them to generate controlled vibrations. Our main focus will be on two prominent types of exciters, that are mechanical and electrodynamic exciters. Understanding how each achieves its purpose is the important discussion in this video lecture. So, what exactly these exciters? In essence, they are specialized devices meticulously designed to impart a controlled oscillatory motion onto a test object. Think of them as the source of very specific and intentional shaking. This controlled excitation is the key. By precisely controlling the vibrations that we introduce, the engineers can gain the invaluable ability to analyze exactly how a structure or material responds to a dynamic loads. This allows us to simulate the complex vibration environments that this object might encounter in the real world, whether it is the vibrations experienced by an aircraft wing during the flight, shaking of a building during an earthquake, or the oscillations within a running engine. It is important to note that vibration excitators aren't a one size fits all solutions. They come in variety of forms, each with its own strength and suited for different applications and specific force and frequency requirement of the test. We will be seeing mechanical and electrodynamic exciters only in this course. Let's see one of the classic example of the mechanical exciters, that is the Schoenstatt mechanism. This clever piece of engineering is a prime example of how we can control harmonic vibrations mechanically. We are generating and controlling the two mechanically. At its heart, Kochuk vibration is brilliant in its simplicity. It takes rotary motion, the kind you get from a spinning motor. Here it is a smooth back and forth movement that follows a sine wave pattern, which is the output. The key in controlling the vibration lies in the crank of the mechanism, which is typically driven by the motor. Whether this motor operates at a constant speed or a variable speed, it directly dictates the frequency of the resulting vibration. The faster rotation of the crank means higher frequency of vibration. Further, the physical dimensions of the crank yoke determine the amplitude or the extent of the back and forth movement. Look at this figure. You can see a simplified representation how this might be applied. Here the Schottchuck mechanism driven by the motor is generating a oscillating force denoted as F equal to m omega square sine omega t, where m is the mass of the rotating motor, omega square is the operating speed of the motor, r is the radius of the crank, omega is once again the rotating speed, and resulting a displacement of x of t, that is r sine omega t. R is the displacement of the object, whatever which is going to be kept at this table. Otherwise, here it is going to be the car, and omega is going to be once again the motor speed. Note, it is very important mechanical excitators are using elastic spring force, particularly suitable for low frequency applications, that is typically below 30 Hz, and the load which is under 700 Newton. Building upon our understanding, it is important to realize that the harmonic force generated by these mechanical excitators can be applied to a strict structure in a couple of ways. As we saw in this illustration, it is act as an inertia force, directly shaking the mass. Here, the car is directly connected to the Schottchuck mechanism itself. That is, it is directly shaking the mass. Alternately, we can also connect it to a spring, that is elastic spring, where the oscillatory motion is transmitted through a spring element. However, this type of mechanical excitators are typically having a very low range applications in terms of low frequency and lighter loads. Think of simulating a sway of tall building of the low rumble vibration in certain machineries. They also tend to be employed for lighter load requirements. Trying to shake a very massive or stiff structure mechanically can become quite challenging and may require significantly larger and more complex mechanisms. So, while they are valuable tools in the vibration testing, their strength lies in the realm of lower frequencies and lighter loads. This slide, we are going to see the another way the Schottchuck mechanism can be utilized to excite a structure. In this illustration, the rotating motion of the crank is still the initial driver. However, instead of directly applying an inertial force, mechanism are used to generate a sinusoidal vertical displacement. This displacement is transmitted to the structure through the spring. In this case, the wing of an aeroplane is connected through the spring. This setup allows for the excitation of the structure with a controlled harmonic force at a very specific frequency. This frequency is directly determined by the rotating speed denoted omega of the crank, which is driving the Schottchuck. To understand the force which is generated and applied to the spring, we can see the Hooke's law, a fundamental principle in elasticity. Hooke's law states that spring force represented as F equal to stiffness multiplied with displacement. That is, it is directly proportional to displacement as well as spring stiffness. Mathematically, it is written here. Since the displacement generated by the Scotch shock is a sinusoidal function of time, that is, the displacement x of t is r sine omega t, this gives us the force applied to the wing by the spring as a function of time. This demonstrates how the mechanical motion is translated into a controlled sinusoidal force applied to the stress structure through the elastic properties of the spring. Now, we explore another ingenious method for generating mechanical vibrations, that is, use of counter rotating masses. The fundamental principle here is the creation of a controlled unbalanced forces. Imagine two identical mass rotating at the exact same speed but in opposite direction. As these masses while around this respective axis, they each generate a centrifugal force. Interestingly, while the horizontal component of these forces constantly oppose and cancel each other, the vertical component synchronously added up. This clever arrangement results in a net vertical force that oscillates up and down. This type of exciter is particularly advantageous because it can generate relatively larger forces. This makes it is well suited for testing heavier structures where more significant excitation forces are required to induce measurable vibrations. The magnitude of this resulting vertical force can be mathematically described by the equation, that is f of t equal to 2 times of mass r radius of the rotation into omega, that is angular velocity, multiplied by 2 times of cos omega t. This the rotation is in the form of sine cosine wave here, with omega is going to be the angular velocity. By adjusting these parameters, we can control the output force. The figure here shows a typical setup where two counter rotating masses are mounted on a structure. In this case, it is a building frame supported by columns and it has a girder. The generated vertical force is shown, which is acting on the girder. As indicated at the bottom, this method is capable of generating substantial large vertical forces ranging from 250 Newton to 25,000 Newtons, highlighting its capability for testing larger and more robust structures. Now, let's shift our focus to a different type of vibration exciter, electrodynamic shaker. Interestingly, an electrodynamic shaker can be thought of as operating on the reverse principle of electrodynamic transducer. Like a loudspeaker, a fundamental principle behind its operation lies in the interaction between electric current and the magnetic field. When an electric current flows through a coil of wire that is placed within the magnetic field, it generates a force. The magnitude of this force is directly proportional to several factors: current flowing through the coil, intensity of the magnetic flux, and the length of the coil. This generated force is then utilized to accelerate the shaker table. This table is the platform upon which the test object is securely mounted. By controlling the electric current flowing through the coil, we gain precise control over the force applied to the table. Consequently, the vibrations transmitted to the test specimen. This relationship between generated force and the electrical parameters as expressed in this equation, that is F equal to D times of I multiplied with L, where D is the magnetic flux intensity, I is the length of the coil, and L is the length of the coil, I is the current. Let me see this shaker, a coil which is part of the moving element, a coil which is part of the moving element attached to the exciter table. This is the exciter table where the mass M is suspended within the magnetic field produced by the strong magnet. So this is the magnetic field which is producing the strong magnets. The flexible support is here. This is a flexible support allows for a controlled vertical movement. When current flows through this coil, when current flows through this coil, it interacts with the magnetic field, generating an upward or downward force F, causing the table and the test object to vibrate. Delve deeper into the construction of electrodynamic shakers. We find that they employ a moving element. This assembly typically includes current carrying coil, shaker table itself, which is suspended by flexible supports. This suspension system is crucial as it ensures that the motion of the table is primarily linear, providing a well-defined direction of testing. The source of the magnetic field within this shaker can vary depending on the size and intended application. For small shakers, we utilize permanent magnets to generate the necessary magnetic field. These are compact and reliable for lower force requirements. However, for larger shakers, we need to produce substantial force. Electromagnets are typically employed. Electromagnets allows for greater control over the magnetic field strength, which in turn enables the generation of higher forces. The acceleration achieved by the shaker table and consequently by the test component mounted on it is directly influenced by the maximum current that can be driven through the coil and the total mass being accelerated. This total mass includes both the mass of the test component itself and the mass of the shaker, which is a moving element. Higher current will result in a greater force. That is, the input current is dictating the force, therefore, which is leading to higher acceleration for the given mass. Conversely, a larger total mass will result in low acceleration for the same applied force. Further, the nature of the electrical input current, which dictates the characteristics of the output force and therefore the vibration. If we supply an AC, that is alternating current, to the coil, it will produce a harmonically varying force resulting in sinusoidal form. We often use it for frequency response analysis and fatigue testing. On the other hand, if we apply a direct current, that is the DC current, it will generate a constant force which can be useful for static or quasi-static testing scenarios. So, to summarize, the acceleration we can achieve with an electrodynamic shaker is fundamentally dependent on the current we can drive through the coil and the total mass that need to be moved. The important characteristic to understand about the electrodynamic shaker is that they exhibit two primary resonance frequencies. One of this is associated with the stiffness and mass of the flexible support system that suspend the moving element. The other resonance frequency is related to the mass and stiffness of the moving element itself, including the coil and the shaker table. Looking this graph, we can see how the acceleration response of the shaker changes with frequency. Notice the two distinct peaks in the acceleration curve. These peaks are corresponding to the natural frequencies or resonance frequencies of the flexible support and the moving element itself. At these frequencies, even a small input force can result in a large vibration amplitude, which can be undesirable for controlled testing environment. Therefore, effective and typically recommended operating frequency range for an electrodynamic shaker lies between these two resonance frequencies. The shaker provides more consistent and controllable acceleration output for a given input current. This is the region where we can achieve relatively constant acceleration as we sweep through different frequency. Electrodynamic shakers are quite versatile and powerful. They are capable of generating significant forces, often up to 30,000 newtons, and can achieve substantial displacement up to 25 millimeters. Moreover, they can operate over a broad range of frequencies ranging from as low as 5 Hz to 20 kHz. This wide range of capabilities, combined with their excellent controllability over the amplitude and frequency of vibration, makes them widely used in a vast array of vibration testing applications across different industries. Vibration excitators are also known as shakers, are crucial tools for determining dynamic characteristics and conducting static testing by imparting controlled oscillatory motion or force. Mechanical excitators like the Scott chuck and counter-rotating masses convert rotary motion into linear or vertical vibrations and are often used for lower frequencies and lighter to moderate loads. Electrodynamic shakers, operating on the principle of electromagnetic force, offer a wide frequency and force range by using current in a magnetic field to drive a moving table. These shakers have resonance frequencies related to the suspension and moving element, with optimal operation occurring between these points. Their versatility and controllability make electrodynamic shakers widely applicable in various vibration testing scenarios. Thank you for being with this lecture to explore the principles and applications of vibration excitators with me. I hope this overview has been informative. It was a pleasure discussing vibration excitators. If you have any more questions in the future, feel free to ask. Once again, thank you, one and all.